So good morning, good afternoon, whatever the time is. And we will start in a second. The first thing that I will give you is our webinar link. The webinar run is right here. So it is this link. Okay. And I'm giving you that link. And hi, Juan. And I'm allowing everybody to talk. And here in chat, I'm giving you the link. And some of you already have the link from the previous time. So that's nice. And you can follow. We are right here. March 16, 12 to 1. And what I wanted to show you are the labs that I created while by mostly copy and pasting, and also talk some more about quantum computing. So I'll do three things, I think. I'll show you the new books. No, I heard somebody, that's nice. Okay, I'll show you the new books. I will show you some news, and then we'll look at the lab, okay? So the books. First of all, okay, people are coming, that's nice. Okay, and everybody can talk. First of all, you probably should be aware that there is such thing as a Qiskit library, the Qiskit tutorial. So I absolutely need to give that to you because you're, let's find it. That's really the best tutorial, as I maybe told you last time. I went through a lot of trouble trying to understand this quantum computing, and I'm honestly telling you that, but the end result is least I can start the conversation. So that's the major link. If you just go there, you will see that there is a complete manual. Okay, and I'm giving you that manual, and I think I should also keep it here. Well, maybe this way, right? IBM uppercase, IBM tutorial. And I think that is the best tutorial. Now, the tutorial goes and shows you the links on YouTube, so you can enjoy the lectures by amazing people there. And I think that I'll give you that link also. It's Qiskit here. Okay. And I'm giving you that link as well. Yeah, these are your resources. Okay, and then I may be repeating myself, but I told you that I went essentially through all of the tutorials, and it was on whatever the name of it. Okay, I won't even name it. That was the tutorial on quantum computing. Well, simply spoken, don't use it. The guy speaks very slowly to fill up the time and writes every word as he speaks it, and just a waste of time. So even though I connected to him on LinkedIn, ignore that, go for this and go for that. Now, when you go here, that is the best guy right here. You see him, John Watrous. That's a very interesting name, John Watrous. He has only 4 lectures. They are complete, very technical. Everything in quantum computing, very technical. I'm trying not to be that way. Okay, so far we're not that way. Now, this girl by the name of Olivia. She shows her favorite books. These are great books. I bought them. Here they are. Here's a book on quantum physics. Okay, I hope you see that. It is somewhere beyond just a high school grad interested in the thing and approaching the college, and it's called Quantum Physics, What Everyone Needs to Know. What Olivia special liked about this is that everybody needs to know. That's number one, and I'm almost done with this. You can get it on Audible, and it is free with Audible. Now, the next book is this. It's called Totally Random, Why Nobody Understands Quantum Mechanics, and it is cartoons. So in these cartoons, you have characters. Characters are like this. So this character is called not Einstein, but Einsteinish or Einsteinish. And so the other guys are also called this way. This is similar to the slides that I gave you, a funny explanation. Then there is the strange world of quantum mechanics. All very recommended, and 6 ideas that shaped physics. The guy wrote 6 books, that's one of them. That is the one on quantum physics. So 6 ideas, this idea is particle behaves like waves. Now, what personally struck me when I was listening to this quantum mechanics was the fact that all electrons are the same. Even though I couldn't yet convince anybody that that is groundbreaking. Look at cookies, they're all different. Look at faces, they're all different. Look at bricks, they're all different, but all electrons are exactly the same. I still cannot believe it, but that is reportedly the truth. Now, that is an introduction of a news. Now, the next thing that I will give you is the slides, and the slides are right here. So here you are. If you're on Quantum Webinar, then that is a link to the folder. So if you want to go to the folder, you will see the introduction. We didn't do all of the introduction last time, so we'll do a bit more of the introduction. Okay, it's already downloaded here. It should be right here on my desktop. And if it's not, we should download it here right now. So I'm downloading it. There you are. And I'm putting it on my desktop. I don't understand why it's shaking me for my PowerPoint, because it's probably attempting to open it. I will pull a rug from under it and I will put it on the desktop. Wow. Okay, I can't, but I'll just use this. But before I do this, here's the latest, well, it is an advertisement. Latest advertisement that I just saw. It came from here, Wells Fargo. And I think that's very honest. It will tell us quite a lot of real truth, because many people ask me, does quantum computing really exist? Is it possible? All these miracles that they're talking, and is it possible to really program it? Well, today I'll show you how you program it, but is it practical? Well, this is an honest answer. Short answer is not yet. Now, this article is, let's make it bigger, by Wells Fargo Chief Information Officer and Head of Digital Technology Innovation. Essentially, what he is saying, we're preparing for the revolution that will happen 10 years from now. Now, that will probably happen sooner. I'm reading one of the physics books, the one that I showed you, this one. And he's writing it when the computer was not built yet. He said in 2017, he was saying, well, maybe in 10 years from now. Now, he was wrong on that. We are 6 years from when it was, and the latest, greatest IBM computer is 433 bits, and the speed is increasing. So maybe this guy is also wrong on about 10 years from now. But at least the whole story is that, and that's why we don't have that many people, because it's very early and not everybody is interested in something that will happen. But some people are, okay? And please ask the questions if you have them, because we should discuss, otherwise why are we here? Okay, 5 points that he says, what is quantum computing? Well, we know it's you build your computers on electrons or some other little thingies like that. There are 4 different ways to build your computers, and they look like this, very nice, yes. And we know what's quantum computing, plus here's a picture. That's what the quantum computer looks like. And I believe it's using superconducting and super cool temperatures so that those electrons wouldn't run away. But each electron represents a bit, or in this terminology, it's a qubit, it's a quantum bit. And the biggest difference between a regular bit and a qubit is that a bit is either 0 or 1, and a qubit is either 0 or 1 or anything in between. And because it can be anything in between as long as you're not looking at it. So because it can be anything in between, it can try all possible combinations at all time, as long as you honestly don't look at it. Now, it sounds unbelievably strange to me, but all the books that I read, they agree about this, and all the scientists that write those books also agree about this. That is why you see a lot of consternation among all scientists. And there are 4 theories from the Shiva is dancing in every elementary particle to just shut up and calculate. There are theories and you can accept any one of them, but the end result that it works. So why does it matter? Well, because it matters because you can calculate exponentially faster. And exponentially fast means the number of qubits that you have, you take 2 to that power. In other words, let's say, well, let's bring the simplest possible word so that you will believe me at least on what I'm saying. What I'm saying is that I need a okay, so I need 2. That will be 2 to the power of q, where q is the number of qubits. So in the current Osprey computer by IBM, q is 433. Q is 433. Now, how much is that? How much is 2 to the power of q? There is a very simple way to calculate this, and that is simply 2 times 2 . Well, okay, and this is 8. Everybody would agree with that. So, well, if we take those groups and multiply it by this, that means that we need to take 433 and divide it by 3. Well, if you divide it by 3, it's about 150. Okay. So you need this group. So instead of 2 to the power of 433, in other words, let's put it like this. 2 to the power of, maybe I'll put it like this. 2, 4, 33 is the same as 8. And now you divide 433 by 3, and that's, I said it's about 150. That's a little less, but let's say it's about this one. Now you remember it's about this. But I also want to substitute 8 by 10. It's close. We rounded this number up and this right up. I think this is down, but it's close enough. 10 to 150. Now, do you know how many particles are there in the world? Who knows how many particles are in the world? I will open the chat. And who can tell me how many particles are in the world? Okay, who tells me first? A little competition here. Okay, well, what if we Google that? Because if I give you the number, you may not believe me. So far, nobody says anything. Okay, here you are. Number of particles in the universe. It knows what I want to ask. And the answer, about the 100, right? Okay, well, I also had this number about 100 or 90, but what they say, cosmic abundance, who knows, but about 1,000. Let's just verify. You say, okay, so that's the commonly accepted number at 10 to the 86. It's about 100, Daniel. Daniel is right. And that I don't quite believe. But whatever it is, let's go to this here. Well, if it is like 10 to the 80 or something like that, well, we have so much more combinations that you can represent by 433 qubits. Before, people would argue that, oh, you cannot break my encryption because you need to have a computer that would have as many particles as there are in the universe, and there are only 10 to 86 particles there. Well, somehow this simple and winning argument was faulty, because you can see that it doesn't matter how many particles you have. It matters how many combinations you have, and how many combinations is 10 to the power of 86. But we have more, so we can calculate everything that's in the universe and so on. Okay, if that is the case, we were right here. We see why it matters. That computer should be able to calculate things. That's why it matters. Then he says what impact it will have on banking. Well, sorry to say, but it's building his career. I think that's the major impact of what he is saying. Meta is saying that, but he's saying that, oh, we will be able to do know your customer and anti-money laundering. There are no algorithms to do it as yet. And you need an algorithm for every computer problem to be solved on qubits. I'll show you one. I won't be just blah, blah. So I'll show you one. but every one of them has to be designed. That's not your regular programming exercise where you say, oh, the program should do this, and then you ship it off to the cheap place. No offense to cheap places, just happens that the price of programming is lower there. So sorry to say, no, you need a Nobel laureate kind of a guy who will create an algorithm for you, and then you will be able to do it. So he is a little bit, but of course he wants to say, oh, we are great, we are doing this. That's the real truth. I think is written today, something like this. So what is Wells Fargo doing? We already told my opinion. Joined the IBM Quantum Network. Well, I also joined the IBM Quantum Network, so I'm also doing something great about this. When will it be practical? That's the important questions you should have asked it first. And he thinks, well, where does he say? 10 years, maybe? Okay. Well, I hope I didn't lose or dampen your enthusiasm because it's kind of there. It just takes a little time. But given these numbers, we can wait. So now practically, here is the slide. Let's go through the slide again a little bit. And now that's real. Before it was just talk. At least it's real in the sense of the slides. You can get the slides, you can download them. That is quantum computing for babies. No joke. And now you know quantum computing. Watch it yourself. Now, this is a cartoon explaining quantum entanglement as if mom discovers that her son is reading some book and it's time to talk about quantum computing. And it says, I know what particles are doing when nobody's looking. And that is also funny. But that we looked at last time. Now, this is a simple experiment done in the beginning of, I believe, 19th century, so 18 something. Anybody can do it. So you send some light. There are two holes. So what you expect is that light will get in here and it will get in here. Maybe a little interference at the edge because light is straight, goes straight right here. And what they found is that that's because light is, of course, made of photons, even though at this time they didn't know photons, but it still goes straight. And what they discovered is the third very dense light line. So they said, oh, no big deal. Particles sometimes act like waves. That's on this book here. Particle behaves like waves. So kind of no big deal, but babies know that, right? But it's hard to understand. Is it really particles or is it waves? And this here is very practical description that first of all will compute faster, that Moore's law doesn't allow us to build faster computers, that it all depends upon research, that it will be a basis for very secure communication, not encrypted by RSA, but encrypted in a quantum way. That one is the first real problem that's solved. So that is of major interest to hackers because if everybody becomes in quantum encryptor, then there's no point breaking RSA. But if you still want to do it, that will allow you to break RSA. When? A few years from now. You can optimize a lot of things where there is no good solution, but you need to go through all of the combinations. A few other implementations are for material science. Material science is trying to create special molecules that will work. And you should create this molecule in the lab and then try it. Well, that's too hard. So let's use a quantum computer and it will quickly create all molecules and try them. And a quantum computer makes mistakes. That's very important, but not a big deal because scientists figure out how to correct those mistakes. So you will have a few molecules that you can try, but that doesn't sound too hard. There's a big list. I would mention drug development, but honestly, I'm not hiding. It's hard for me, hard to understand. And every one of these applications is correct. But the question is, when does it become practical? And it has not become practical. I don't think there is one, I think it's called quantum advantage, one practical application that works and gives an advantage over regular computing. Okay. And that is that link that I gave you, and these are the labs. So today I will show you a couple labs that you can run today. Just don't turn that switch where you're asking to run on real hardware. Say instead you're doing an emulator, because quantum computing is real as far as price is concerned. It's $60 per second. So I don't think anybody will accidentally turn it on unless he really means it. Okay, these are the slides. These are the labs here. Now, these labs are found, in this case, it's on a local host, my computer, but in the quantum computing webinar, it gives you the link to quantum computing labs. So let's open that. Okay, it goes in chapters and you can go inside. This is GitHub, which shows you how the Jupyter Notebook, this is IP1 with Jupyter Notebooks. So I think it will show you nicely, even though we don't understand how that works, but it talks and then gives you a link. And this link, I also think they work. No, they don't. That's interesting. Okay, we're not upset. Some link are broken. Okay, maybe they are really working in the real situation, but that is code. Now you cannot run this code here because this is a GitHub, a repository for storing your code. But yes, you can run it here. And what it's talking about, these are the elements of the computations. Now I'm not going to run it, even though I could. I might run it like this. You see, I ran it, I ran it, I ran it, I ran it, and this is really ran it because it shows a star and then one, but this is just import, including the emulator, and then some more explanation. I want to come to something, okay, something more. But I'm not interested in clicking through today. Instead, I want to show you what this lab does. This lab says, we'll go back down. We'll go from maybe Java, maybe you program in Java. So Java, there is a compiler and it compiles into Java bits and Java bytes. Java bytes, they are classical Java bytes. They have bits. Well, really, they're Java codes. So forget all of that. You're too high. Go down. What's inside of bits? Well, that is not even calculator. The computer, even our computer, doesn't have add and subtract operation. Instead, it has only logical gates. Out of this, you construct a register, general register, which is able to do plus and minus. So forget that knowledge either. And in the end, you are back to logical gates. For example, this is a logical gate and it accepts two inputs. And right here, you can do an X. X means not. You can take your input and you can convert it into not input. And you can do it here. Now, that is not quantum computing yet, but it is done on an imitation of quantum computer. Then in the end, you will run through this computation and copy the output into the regular bits. So therefore, you need to create 4 qubits machine and output, I think, 2 qubits, 2 regular bits. So if that sounds a little strange, then here I'll do even better. Eight qubits and 8 output bits. But the essence is not hard. Those mysterious qubits, which we just saw on the article from the bank, these mysterious qubits, they do exist and they can be represented by different things like electrons, and there are some other strange way to represent the physical part of the computer, but the logical part of the computer will be there. And that is me running a simulation of quantum computing, in this case, in Jupyter Notebook. So then we can go on and do regular operations on a quantum computer, but they wouldn't make much sense. It wouldn't make sense to do that, okay? Because here we are creating a quantum bits, qubits, and copying the output to a regular bits, and now we can use it. But as you can see, it's an amazingly primitive thing, right? You wouldn't expect to be programming on that level. Nevertheless, that's true. So here we explain exactly how we add in general in school, and you can imitate this addition in 0 and 1, and then you can imitate it in a quantum computer. Again, I haven't shown you a problem that I would really like to solve. I just showed hello world kind of approach, right? It's talking about how you adding. Now you have an adder, okay? So you're adding with Qiskits, and that's how you should add. And now you solve the hardest problem of math, 1 + 1, and that is 2. Now, if you're underwhelmed, I'll show you a bigger, let's see, nobody said anything. I'll show you the real stuff. So that is the real stuff. This is Professor Shor, who is alive and well, teaching at MIT, I believe, and he invented this algorithm. Again, this algorithm here is using a simulator. So we're still not touching the real thing. The real thing, to touch it, you would have to go to IBM, subscribe, get an account, give the credit card, and maybe you can compute. Okay, but what they say here is we'll explain to you how this algorithm works. And we don't even solve the problem of factoring prime numbers. That's our goal. But it turns out that you can do a simple problem which will help you do that problem. And what you're doing is finding a period of a function. So it explains how exactly you do it. That's the solution. That's real code running on an imitation, and that will actually work because I'm only setting n number of qubits to 35, and that is as far as imitation can go. So imitation can do that. Okay, that's the implementation using Qiskit library. Not that we're going deeply and understanding that as yet, even though I will have to understand it by April 10th when I'm teaching it the first time. And all of that you can get on my GitHub. Okay, or you can go to their own environment, because the environment actually works similar to this, except that now you're running Jupyter, you're running in Jupyter, Now here, I'm running it on my local computer. That's why it works so nice and fast. But that's, you say, local host. But if you run it here, then it also gives you text, allows you to run it, and it runs similar to Google, what's the name? Colab, right? Google Colab. Colab. Like this. If you're not familiar with that, then you can also run notebooks here, except that this works a little bit better. And if you pay $10 a month, it works even better. You can run it here and it will guaranteed run. IBM sometimes doesn't quite run. I noticed that. Who knows what is behind their stuff. So that's why these labs run on your local implementation of that. I say it's a better thing, but what can they do? They wanted the simplest possible way, so they do it like this, and you can run it here. And also notes, please, that Qiskit textbook is a new version and it's in beta now. So I personally find that somebody who did the port to the new version today didn't do the good job. So I would still recommend when you see this, do you want to try it now? The new version, say no, because that one is complete and has no mistakes. But the new one, I wouldn't say that. Maybe I'm wrong, or maybe they're still working on that. Okay, now to summarize what I'm saying, yes, there is quantum mechanics where elementary particles are hiding. And I'll stop the share. And if you don't get in their way, they can solve hard problems. In order for them to solve the hard problems, you need to explain what the problem is, and you can do it using Qiskit library, for example. But not everybody can become, maybe I'm letting you down, but not everybody in the world can become a Qiskit programmer or maybe a quantum programmer. Maybe it will change and maybe it will be easier. But right now, every program is a great achievement. But you can run their own programs. So maybe just like machine learning, somebody will run those programs for you. You will just combine the regular hardware and the quantum hardware, and it will be practical. That is the essence of what I want to say. Honestly, I'm not sure if we will continue the series, right? So now, if you guys, all of you, if you say yes, please continue the series, we can. But given that on Fridays I also do OpenAI, so if we say here's the quantum computing, now go to trend. Okay, and if here I'll put quantum computing. And if I want to compare it with OpenAI, and we started from Hugging Face, so we will include Hugging Face. Okay, then you see that quantum computing is quite lower. But you know what? Today it's better. Today it's a little bit better. Let's add Hugging Face. But quantum AI, every journalist needs to write about this. What did he say in the morning? Hugging Face also suffers the same fate as quantum computing being dwarfed by OpenAI. However, let's do this. And we say amazing results. I don't see any correlation, but I see they are quite similar. So today I'm of two minds. That's what the electrons are. They are of two minds, and they don't know if they're facing up or down. So me too. And that, oh, I'm not showing that listing. I wasn't showing. So let me show. There you are. What I was showing you is that if you compare quantum computing and popularity, well, that's not for everybody, but it's powerful. Well, this is Hugging Face. This is how you make OpenAI. Well, it's also not for everybody, but it's similar. So that's an argument to, yes, continue quantum computing, but I would still like to get your vote. In other words, here's the chat. So Jose gave us the calculation. Oh, very nice, thank you. Okay, and Daniel offered a number of particles in the world, and we continue the you see. Hey, let's see what the output will be. Now I'm measuring in terms of quantum computing. Up until now, you were doing something that nobody observed, but now we're measuring the result. I don't see any votes. So on this contingency, I prepared everything that you need to go on your own. And that's all of that. Whatever this says, if we don't continue, okay, Jose says, sure, why not? I'll tell you why not. That's because I also need to prepare for the AI on Thursday. But so what? What do we exist for? Maybe I should be doing. So at least one vote for yes. Can we get more votes? 2 votes. Just one more. I know I'm being picky. 2 is good enough. And I said 2 is good enough. And Daniel, you raised your hand. That's somewhere else, but interaction. Well, let's say we do continue. I'm convinced. Okay. Was it useful? Do you have any questions? Thank you, Renty. Well, honestly, that works. It's a rehearsal. Okay, Kenneth, thank you. We'll continue. But anything else you would like to see?
Well, this is Ken. The more you can focus on practical applications is what interests me.
Well, as I showed you today, you just learn for the future. Even though IBM has the price and everything looks like it's real, but I don't see quantum programmers on Indeed.
Yeah, I mean, I think the kind of problems it's aimed to solve are ones where there are lots of choices.
But when it happens, then they will hire a lot of such people. So okay, it knows that much. But of course, not in Houston, Texas, where I live. We need to say USA, maybe. Oh, let's not say anything. Okay, you can get a job in California in researcher. How many total? Oh, 1,200 jobs and a good salary. I cannot believe, but that's real. Okay, so it makes total sense. I cannot explain exactly what people do, given that programs are not practical, but they exist, they are here, you can run them. And so maybe we're missing, and what we're missing, that's exactly what we will find out. But at least it says here 1,200 jobs. Okay. So it was a pleasure interacting with you guys. Do you know what was Z-Wave attempting with quantum annealing? That is a great thing. Let's record it. And we'll talk about it next time. And I think that was awesome. So thank you very much. I wish you a great afternoon. Not as high, look at that. But there was some good salary, and that's a university. 70 to 110, not much. Of course, yeah, as smart as required, then you can get a different place salary. But you know, once I traveled and I was teaching at Boeing, and these people were very smart. And I asked them that question exactly. I said, how do you get those smart people? And they say that we tell them, what do you want? Do you want to sell more diapers? Go work for Amazon. You'll get a high salary. But you want to put the man on the moon? Come here. And that was an interesting thing. I'm sure they do it on everybody. So maybe you so much love doing this quantum algorithm research, and it may explode. It may be you will get a Nobel Prize. So maybe people go for low salaries. Quantum computing architect at MIT, and it's very prestigious. Look, you tell friends that you're working on quantum computing at MIT, you got it, right? Okay. Subject matter expert to 200,000. No, not bad. Okay, so thank you, everybody. Thanks a lot. And we'll continue.
Thank you, Mark.
My pleasure. Thank you. So going back to my books, you know which ones. I'll do cartoon now. The next one is cartoon. Okay. Goodbye.
Bye-bye.
Yes, goodbye.